Hi students, good morning. Welcome to the new session of physics classes. During the last class, we have talked about electric potential, and we have defined electric potential as the scalar equivalent of electric field, and we have measured the potential as the work required to bring a unit positive charge from infinity to that particular point. So that work done is a scalar quantity, so you can easily convert the electric field into its scalar equivalent, which is electric potential. We have already said that electric potential is a scalar equivalent of electric field intensity, but we didn't define the relation between electric field intensity and the electric potential. So now today we can start with that relation, that is the relation how electric field intensity is related to the electric potential, or how you can derive electric potential from electric field intensity. Simply the relation between electric field intensity and electric potential. Let us see. See the diagram. The diagram shows a dipole of charge q and length the diagram shows a point charge plus q and its electric field, and its direction is given by that arrow mark, and between or in within that electric field you can find two points A and B. Point A is at a distance r from q0, and the point B is at a distance r plus dr from q. Q is the source charge. From this q, A is at a distance r and B is at a distance r plus dr. At the point B, you are having a charge q0. At the point B, you are having a charge plus q0. And if you are placing plus q0 at B, obviously it will experience a force. And that force is given by this F, and it is acting away from source charge plus q. Okay, we are having a source charge plus q. From there, at a distance r, a point A is there. At a distance r plus dr, a point B is there, where we have placed plus q0 charge, and it experiences a force F away from plus q. Okay, this is the situation. Okay, since q0 is placed within an electric field whose electric field intensity is E, q0, the source test charge, is placed within an electric field where the electric field intensity is E. So by the definition of electric field intensity, that q0 will experience a force. What will be the force? That force is given by F is equal to q0 into E. That we have already established this relation. F is equal to q0 into E. So suppose if you are moving q0 from B to A through a distance dr, you have to do a work against the force F. Are you getting me? Because the force F is acting away from plus q, and if you are moving the charge from B to A, you are moving, or you are bringing the charge plus q0 from B to A, means you are moving towards the charge, but the force is acting opposite direction. So you have to do a work against the force so as to bring the charge from B to A. So for that you have to do a work. So that work for moving q0 from B to A through a small distance dr is given by dw is equal to F into minus dr. Why it is minus dr? You know, F and dr are acting in the opposite direction. So dW is equal to F into minus dr, but F already we have taken as Q0 into E. So dW is equal to minus Q0 into E into dr. Okay, what we have done, we shifted plus Q0 amount of charge from one point to another within an electric field. Now we can remember the definition of potential and all that you keep in your mind. Remember what we have done now, we have kept or we have moved a charge from one point to another within an electric field. Just think whether we have moved a unit positive charge or any other kind, amount of charge. And what is the definition of potential? Definition of potential is work required to, or definition of potential difference is the work required to move unit charge from one point to the other. The potential difference between 2 points is the work required to move unit charge from one point to the other. So if you are bringing, here we have brought Q0 amount from B to A, Q0 amount from B to A. For that you have to do a work dW. So we can calculate dW by Q0. What will be that? dW by Q0 from this equation is equal to minus E into dr. But dW by Q0, that is the work done per unit charge. Work done per unit charge. By the definition of potential difference, dW by Q0 is dV, the potential difference between those 2 points B and A. Is it clear? dW by Q0 is the work done per unit charge. By the definition, work done per unit charge is the potential difference. So this is the potential difference between the points where we have shifted the charge. So dW by Q0 is dV, which is the potential difference between those 2 points. So when you are comparing above 2 equations, we can write minus E dot dr is equal to dV and E is equal to minus dV by dr. Minus dV by dr. E is equal to minus dV by dr. What is dV by dr? You can write it as d by dr of V. D by dr of V. By the definition of differentiation, it can be taken as d by dr of V. What is V? The potential. What is R? The distance. So you have taken derivative of potential with respect to distance. Derivative of potential with respect to distance. And last year also we have used this derivative with respect to length or derivative with respect to distance. Derivative with respect to length or derivative with respect to distance is known as the gradient. We have defined that gradient. So minus d by dr of V means gradient of potential, which means potential gradient with a negative sign, that is minus dV by dr. So minus dV by dr represents negative gradient of potential or negative potential gradient. What is that? That is equal to, what is in the left hand side, electric field intensity. So electric field intensity is negative potential gradient. That is a very important result. Electric field intensity is negative potential gradient. Negative potential gradient. That is E is equal to minus dV by dr. That is the relation between electric field intensity and potential, where electric field intensity is the negative potential gradient. We have done nothing. You have chosen a test charge Q, its electric field. Between those between 2 points within that electric field, you have moved Q0 amount of charge. For that, how much work you have to done? That is dW is equal to F into minus dr, because you are doing a work against the force acting. So you have to calculate what should be the work required per unit charge, that is dW by Q0. By definition, that is potential difference. And from there you have got the equation dv is equal to minus E dot dr, or E is equal to minus dv by dr, which is the potential gradient. That is, E is equal to minus potential gradient. Okay, we have defined the relation between E and V. I think it is clear. E and V, that is electric field intensity, is gradient of negative gradient of potential gradient. That means suppose the potential difference we have defined as the work required to move one charge from one point to the other, unit charge from one point to the other. That is the definition for potential difference. Suppose you have an electric field, you have a region within an electric field, and to move charge from one point to another over that surface. Suppose you have a surface, and on that surface we can consider 2 points, and to move a unit positive charge from one point to another, that means from that one point to another point, no work is required. Is it? Suppose you are having a surface, on that surface you can consider 2 points, and to move a charge between these 2 points, no work is required. No work is required. Then what will happen? What is electric potential difference? Electric potential difference is the work required to move unit positive charge from one point to the another. But here, in a particular surface, to move unit positive charge between the points, no work is required. So what will be the potential difference between these 2 points? Potential difference between those 2 points will become 0. That means there is no difference in potential. Listen to my words carefully. There is no potential difference between those 2 points, since no work is required to move unit positive charge from one point to another over a particular surface, which means there is no potential difference between those 2 points. If there is no potential difference between 2 points, what it indirectly indicates, both the points are having the same potential. Is it? Then only the potential difference will become 0. Suppose the 2 points are A and B, and the potential at A and B are VA and VB, and if the potential difference is 0, means VA minus VB or VB minus VA is equal to 0. By simple logic. If VA minus VB or VB minus VA is equal to 0, which means VA equal to VB. Are you getting me? Which means there are certain surfaces over which for moving a charge no work is required. There are some surfaces or some regions over to move charges no work is required, which means over that surface all the points are having the same potential. Over the surface all the points are having the same potential. Then only if you are considering any 2 points, the potential difference will become 0. Is it? So such surfaces over which the potential remains constant. Such surfaces over which the potential remains constant. Such surface is called equipotential surface. Such surface is called equipotential surface. So how you have defined equipotential surface? You have considered a surface. You have considered 2 points, any 2 points over that surface. You have moved one unit positive charge from one point to the another. No work is done, which means there is no potential difference, which means both the points are having the same potential, which means such surface is a equipotential surface. I will show you the definition. See, any surface over which the electric potential is same everywhere is called an equipotential surface. Any surface over which the electric potential is same everywhere is called an equipotential surface. So over an equipotential surface at any point the electric potential will remains the same. Okay, so that is the property of, that is the definition of equipotential surface. And now we can see some properties of equipotential surface. Some properties of equipotential surface. So the first property says no work is required to move charges over these surfaces. That we have already seen. In that sense only we have defined equipotential surface. That is, no work is required to move charges over this surface. No work is required to move charges over these surfaces. Second property, electric field and field lines are perpendicular to this surface. Electric field and electric field lines are perpendicular to this surface. You can imagine that when an electric field is there and electric field lines are there, that direction of electric field, which is denoted by electric field lines, they are perpendicular to an equipotential surface. And the third property is they are closer where electric field is stronger. You can consider within an electric field, you can consider many equipotential surfaces. If you are considering a surface normal to, electric field or electric field lines, that surface should be an equipotential surface by the second property. Second property says electric field and field lines are perpendicular to equipotential surfaces. So if you have chosen a surface which is perpendicular to the electric field or electric field line, that surface should be an equipotential surface. So the region where the electric field intensity is more, there the equipotential surfaces will be closer. Okay, density of equipotential surface is more where the electric field intensity is strong, and they will not intersect. Two equipotential surface will not intersect. So these are the properties of equipotential surfaces. No work is required to move charges over these surfaces. Electric field and electric field lines are perpendicular to these surfaces. They are closer where electric field is stronger, and they will not intersect. So any surface over which the potential remains constant everywhere is known as equipotential surface. And these are the properties of equipotential surface. Okay. Okay, now we have seen what is electric potential, then the relation between electric field and electric potential. Now electric equipotential surface. Suppose you are having an electric field, and at a particular point in an electric field we can define its electric potential. And electric potential is the work required to bring unit positive charge from infinity to that particular point. That is the electric potential at that particular point. Suppose you have a charge surrounding it, an electric field is there, and within an electric field you consider a particular point where you have a potential V. You are placing Q0 amount of charge at that particular point where the potential is V. Listen carefully. You have already a point within an electric field where the potential is V. And you are placing Q0 amount of test charge at that particular point. What will happen to that Q0? That Q0 will acquire some energy. Because the charge is placed at a potential point. That charge will experience, or it acquires some energy since it is placed in an potential point. So what will be, or how much amount of energy it will possess, or what energy it can acquire from that particular point, that is measured as the product of charge and the potential at the point where it is placed. Are you getting me? Simple words we can say, if a charge is present in a potential point, if a charge is present in a potential point, it will possess an energy which is measured as the product of charge and the potential at that particular point where it is placed. In this case, energy is measured as the product of V and Q0, where Q0 is a charge placed at a point where the potential is V0. V, where the potential is V. We have placed a charge Q0 at a point where the potential is V. So the energy possessed by that charge will be measured as V into Q0, where V is the potential and Q0 is the charge placed. And that energy possessed by a charge when it is placed in a potential point, that is known as electrical potential energy. So electrical potential energy is measured as the product of charge and the potential of the point where it is present. That is electrical potential energy. And this is the case when you are considering only one charge. What is the potential energy of a system of charges? What is the potential energy of a system of charges? Here you have got a hint that how a charge is acquiring energy, potential energy. A charge is acquiring potential energy when it is placed in an potential point. So energy is provided by the potential of the point where that charge is present. Suppose a charge is present somewhere where there is no potential. Is that charge acquire some energy? Not at all. Because if you are multiplying Q0 with the potential at that point is 0. So automatically the energy possessed by that system will become 0. Charge will become 0. So I repeat, energy of that particular charge is provided by potential energy, especially the potential energy. Potential energy of that charge is provided by the potential of the space where that charge is present. If the charge is present in a non-potential region, it will not acquire any electrical potential energy. If the charge is placed within a region where there is a potential, then only it will acquire electrical potential energy. Is it clear? Now we can go for the potential energy due to a system of charge. Okay, you see, the electric potential energy of system of charges is the work that has been done in bringing those charges from infinity to near each other to form the system. Electric potential energy of system of charges is the work that has been done in bringing those charges from infinity to near each other to form the system. Suppose you are having a system of two charges. And those two charges you have to bring from infinity to form that system. Initially, those two charges are at infinity. And you are bringing the charges one by one to a space and you are assembling that system. And for assembling that system, you have to bring these two charges from infinity to their respective points. For that, you have to do a work. And how much work you have to do to bring that charges from infinity to their respective points, the total sum of all those work done is equal to the total potential energy of that system. Are you getting me? If you are assembling a system of charges by taking all those charges from infinity to their respective points, for that you have to do some work. Suppose you are taking first charge from infinity to its point. How much work you have to do? Suppose you are taking the second charge from infinity to its respective point. How much work you have to do for that? Since it is a two charge particle system, work done for the first particle is W1, work done for the second particle is W2, total work done will be W1 plus W2. That total work done will be stored as the potential energy of that system. Still it is not clear. Then we can go for an example. See, this is a system of two charges. This is a system of two charges. This is a system of two charges, plus Q1 and plus Q2, kept at the respective points A and B, and A and B are separated by a distance R. Okay. So, by the definition, we have to find out what is the potential energy of this system. By the definition, the total work required to bring these two charges from infinity to their respective points A and B, that total work done will be the potential energy of the system. So, we can separately find out the work required to bring the first charge Q1 and the second charge Q2, that is W1 and W2 respectively, and you can add W1 and W2 so as to find out the total work required to assemble that system. And that total work done to assemble that system will be stored as the potential energy. Okay, so to bring plus Q1 to A, plus Q1 to A, the work required W1 equal to 0. Why it is 0? Because W1 you can measure as potential at A multiplied by the charge you are placing there. What is the VA? VA is the potential at the point A. When you are bringing plus Q1 to the point A, no other charges are present in the region. Without any charge, there is no potential at point A initially. So, VA initially equal to 0. Therefore, VA multiplied by Q1 will become 0. Therefore, W1 will become 0. Which means, to bring the first charge plus Q1 to the point A, no work is required since plus Q1 is placed at the point A, which is a non-potential point. That we have already explained. Okay, now you are bringing the second charge plus Q2 to the point B, which is at a distance R from A. Remember, now plus Q1 charge is present there at the point A. And at the point B, plus Q1 can provide a potential. Is it? Because B is at a distance R from charge plus Q1. So at a distance R, this plus Q1 can exert a potential. And that potential we can express as VB, the potential at B. So W2, the work required to bring plus Q2 to the point B is W2, which is equal to VB into Q2. But VB is equal to 1 by 4 pi epsilon 0 Q1 by R, that is the definition for potential. And the W2 will become 1 by 4 pi epsilon 0 Q1 by R multiplied by Q2. That means W2 is equal to 1 by 4 pi epsilon 0 Q1 Q2 divided by R. So we have a two particle system and we have calculated the work required to bring those two charges from infinity to their respective points separately, that is W1 and W2. Now you can calculate the total work required to bring both the charges, that is W1 plus W2. And by the definition of electrical potential energy, the electrical potential energy is equal to W1 plus W2. That is U is equal to W1 plus W2. What is W1? 0. What is W2? 1 by 4 pi epsilon 0 Q1 Q2 divided by R. So the net potential energy of the system will become 1 by 4 pi epsilon 0 Q1 Q2 divided by R. Is it okay? So this is the net potential energy of a system. So the net potential energy, the total potential energy of a system is the total work required to bring the charges from infinity to their respective points to assemble that system. Okay, in other words, you can say that The electrical potential energy of a system of charges is the work that has been done in bringing those charges from infinity to near each other to form the system. That is electrical potential energy of a system of charges. So we have defined electrical potential, relation between electric field and electrical potential. Then we have seen equipotential surface. Now we have defined electrical potential energy. So electrical potential energy of a single charge that can be measured as the product of charge and the potential at the point where the charge is placed. And the potential energy of a system of charges is the work required to bring all those charges from infinity to the respective points to assemble that system of charges. Okay. Now, a simple topic is left in this chapter, potential, that is potential of a dipole. Potential of a dipole, electric potential of a dipole. See, I have already told to you, potential is the property of electric field. Potential is the property of electric field. And suppose you are having an external electric field. And within an external electric field, you are placing an electrical dipole of charge q and length 2l. We have already done this with the electric dipole in an external electric field. And you know that whenever an electric dipole is placed in an external electric field, it will experience a torque. When the electric dipole is placed in an external uniform electric field, it will experience a torque. And the torque you have defined as tau is equal to P cross E, Pe sin theta, that we have already done. As a result of this torque, the dipole will get rotated. Suppose initially the torque is there, that is Pe sin theta, and as a result of this torque, this suppose it experiences a torque, and against the torque or due to the torque, the dipole is rotated through an angle d theta. Are you getting me? Already, suppose when you are placing a dipole in an external electric field, it will experience a torque. As a result of the torque, it is rotated by d theta. So how much work is required to rotate that? Tau into d theta. Simply as in the case of force into displacement, here it is force is replaced by torque, displacement is replaced by angular displacement d theta. So dw, that is small work required to rotate through a small angle d theta, will be tau into d theta. Suppose you are rotating from theta 1 to theta 2, what to do to find out the total work done? Integrate dw within the limit theta 1 to theta 2. That we have generally doing. So we have to calculate how much work is required to rotate a dipole in an external uniform electric field from theta 1 to theta 2. How much work is done to rotate the dipole from theta 1 to theta 2. It's very simple. That means you have already, half you have already done. That means what is the torque acting upon the dipole when it is placed in an external uniform electric field. Using that, you have to calculate the work done as torque into d theta. Getting confused? Come, I will show you. See the diagram? An uniform electric field is there. Dipole of charge q and length 2l is placed, making an angle theta along the direction of electric field, and QE, and this diagram is familiar to you. You have already gone through this diagram. I have repeated this diagram only, and you just remember what you have done here. QE is there, minus QE is there, and they are acting in the opposite direction. So it will experience a force, it will experience a torque, and as a torque, it is getting rotated. So the torque acting will be Pe sin theta, P cross E. The torque acting will be Pe sin theta, that is P cross E. Okay, the torque acting is P cross E, that is Pe sin theta. And by rotating through d theta, by rotating through an angle d theta, how much work is required. That work done dW is equal to tau into d theta, which is equal to tau is Pe sin theta. So dW will become Pe sin theta d theta. Simple steps. And this is the work required to rotate through a small angle d theta. And the work done to rotate from theta 1 to theta 2. Work done to rotate from theta 1 to theta 2. W is equal to integral theta 1 to theta 2 dW. That is theta 1 to theta 2 Pe sin theta d theta. So Pe is constant and integral sin theta d theta will become minus cos theta. Integral sin theta is minus cos theta within the limit theta 1 to theta 2. I already told you this negative sign you can neglect when you are interchanging the limit. Actually it is upper limit minus lower limit. So here upper limit will become theta 1 and lower limit will be theta 2 when you are neglecting this negative sign. So W is equal to Pe into cos theta 1 minus theta 2. What is theta 1 here? Theta 1 is the initial angle and theta 2 is the final angle through which it is getting rotated. So when dipole is rotated from theta 1 to theta 2, an angle theta 1 to theta 2 within an electric field, external uniform electric field, the work done W is equal to Pe into cos theta 1 minus theta 2. Okay, where theta 1 is the initial angle and theta 2 is the final angle. Now you see, if theta 1 is equal to 0, theta 1 is equal to 0 means what is theta 1? That I show you what is theta 1. Initial angle made by dipole with the direction of electric field. If theta equal to 0, dipole will align in the direction of electric field. That means dipole will be parallel to electric field when theta 1 equal to 0. So when theta 1 equal to 0, this will become W is equal to P into cos theta 1 minus cos theta 2, where theta 1 equal to 0, where cos 0 will become 1. So W will become Pe into 1 minus cos theta. Pe into 1 minus cos theta. Okay. Then suppose theta equal to 90, which means initially theta 1 is equal to 0. That means initially you are placing the dipole along the direction of electric field, parallel to electric field. Now you are rotating through an angle 90. Now you are rotating through an angle 90. That means from parallel direction you are making it perpendicular. By rotating 90 from parallel direction means you are making it perpendicular. How much work is required for that? That means initially theta 1 is 0, so that 1 will remain there. Then cos theta is 90 and cos 90 will become 0, that will become Pe. Which means to rotate the dipole from parallel direction to perpendicular direction, how much work is required? Pe amount of work is required. How much work is required to make it anti-parallel? That means making 180 degree rotation. From parallel direction, make it anti-parallel. So 1 minus cos 180 is minus 1. So that will become 1 minus of minus 1 will become 1 plus 1. So 2 Pe. Okay. So from the parallel direction, if you want to make the dipole in the perpendicular direction, how much work is required? Pe amount of work is required. From there again you have to make a 90 degree rotation. For making 90 degree rotation, how much work is required? Pe. So Pe plus Pe, that is 2 Pe, that is for 180 degree rotation. Very simple. Is it? So by rotating a dipole from parallel to the perpendicular direction, you have to do a work equal to Pe. To make it 180 degree rotation, you have to make 2 Pe rotation. Sorry, work done. Okay. Okay, now we have seen how much work is required to rotate a dipole in an external uniform electric field. Remember, when you are rotating a dipole in an external electric field, you are doing a work on the dipole. According to work energy theorem, that work done will be adding to its potential energy. That work done is adding to the potential energy. So when you are rotating a dipole in an external electric field, suppose you are bringing a dipole from infinity to a electric field and rotating it, you are doing work on the dipole two times. One time you are doing work to bring it from infinity to the electric field. Second work you are doing on rotating it. So work is done on the dipole to bring to the electric field and rotate it. Both will add as the potential energy of a dipole. Okay. So when you are bringing a dipole from infinity, you have to do a work to bring, because you are bringing two charges. As a dipole, you are bringing two charges. And if you are bringing a charge from infinity to a electric field, you have to do a work. So obviously to bring a dipole from infinity to electric field, you have to do a work. And when it is placed in electric field, it is getting rotated, and as a result of rotation, extra work is done on the dipole. So both those work done will be stored as the potential energy of a dipole. So what will be the potential energy of a dipole? What will be the potential energy of a dipole? We have to calculate that. Okay, so we can go for potential energy of a dipole. Okay, we can go for potential energy of a dipole. Suppose you are bringing this dipole of charge q and length 2L from infinity to this electric field. See, electric field is denoted here. So from infinity, you are bringing this charges to electric field. Two charges. Suppose if you are bringing this dipole, these two charges together you are bringing from infinity to the electric field, and plus q is placed here and minus q is placed at a distance, extra distance 2L from plus q. See, from infinity you keep q here, at an extra distance 2L from plus q you are placing minus q. Okay, if you are bringing both the charges to the same point where plus q is placed, the total work required will be 0, because for bringing plus q charge you have to do a positive work, to bring minus q charge you have to do a negative work. So when you add the two, it will be getting cancelled. So to bring minus q charge to an extra distance 2L, you have to do an extra work. Are you getting me? If both are kept at the same point, no work done will be 0. But for bringing minus q charge at an extra distance 2L, you have to do a extra work. You have to do some extra work to keep minus q at a distance, extra distance 2L from plus q. Is it clear? Listen carefully. Because this minus q is kept at an extra distance 2L. To keep minus q to move minus q at an extra distance 2L, you have to do an extra work which is equal to what is the force on q multiplied by 2L, force into displacement. See, what is the force on minus q when it is placed in an electric field E? That is E into minus q is the force, multiplied by 2L is the distance. So net work done in bringing dipole to the field will be U0. Net work done in bringing dipole to the field will be U0. That is equal to minus QE into 2L, which is Q into 2L, you can take it as P, that will become minus PE. From where this U0 comes as the extra work required to move minus Q through an extra distance 2L. To bring both the charges at the same point, the net work done will be 0. So to bring this minus q through an extra distance 2L, extra work is done. That is the work required to bring the dipole to the field, which is the initial energy of the dipole. Because the work required to bring the charges from infinity to a particular point will be the potential energy. So U0 will be minus PE. Okay, and one more thing, dipole is kept parallel to the electric field. You can see dipole is kept parallel to the electric field. Electric field and dipole are in the same direction. To rotate through an angle theta, work done will be W is equal to PE into 1 minus cos theta. Okay, so that will be adding to the potential energy of the dipole. So initially, I already told you, you are doing two work on the dipole to bring it from infinity to a point, then to rotate it. You have to add both these work done so as to get the total energy of the dipole. So you have calculated what is the work required to bring it from infinity to here, that is U0 this is minus PE, and what is the work done to rotate it, that is PE 1 minus cos theta. So you are adding the total potential energy will be U theta, that means when it is kept, initially you are bringing the dipole parallel to the electric field, from there you have rotated it to theta, now the dipole is deriving an angle theta with the direction of electric field. At that position, what will be the total potential energy? That is given as U theta, and U theta equal to U0 plus W. What is U0? U0 is the work required to bring the dipole to the electric field in the parallel direction. And what is W? W is the work required to rotate through an angle theta. So U0 is equal to minus PE, and W will become PE minus PE cos theta. So P minus PE plus PE minus PE cos theta, minus PE and PE get cancels, that will become minus PE cos theta. So U theta will become minus PE cos theta, that is magnitude of one vector, magnitude of another vector between, and multiplication of cos theta, that is dot product between these two vectors, that is minus P dot minus vector P dot vector E. This is the net work done, that is the total work done on the dipole to bring it from infinity to parallel direction to the electric field and get rotated. What will be that? That is the total energy of the dipole. Okay. So that is the total energy of a dipole. So total energy of the dipole is the work done to bring the dipole from infinity to the electric field along its direction and to get rotated in an angle theta. So you have taken the first work done, that is as U0, that is the energy possessed by the dipole when it is aligned parallel to electric field when it is taken from infinity, and W is the work required to rotate it through an angle theta. So the total potential energy when it is aligned at an angle theta is U theta, and that U theta equal to U plus U0 plus W, and that you have got as PE cos theta minus PE cos theta, that is minus P dot E. Okay. Okay, so now we have gone through the potential of an electric field. So we have defined the potential, then potential due to a point charge, potential due to a electric dipole, then equipotential surface, work done in rotating a dipole in an external electric field, then total potential energy of a dipole, then potential energy. All these matters we have discussed. So we are still in electrostatics, and we have started, remember from where we have started. We have started from a static charge, and what are the properties of these charges. And we have seen different properties of charges. One of the important property is electric field intensity, and we have calculated the electric field intensity using Coulomb's law method, and for continuous charge distributions this Coulomb's law method is not sufficient, so we have gone for Gauss theorem, and using Gauss theorem we have calculated electric field intensity for some special kind of charge distributions. Then we have gone for we have find some difficulty in dealing with the electric field intensity, since it is a vector quantity. Then we have converted that vector quantity into an equivalent scalar quantity. Then now we have derived some or discussed some properties of that potential. Okay, so that's all for today. As I remind you once again, go through the classes carefully, listen to my words carefully, and you can analyze these steps given in the slides, and you can refer to the textbook. Along with the textbook, with the help of our classes, just note down the important points and make a notes in the physics copy. And already I have sent you some homeworks, and go through that solved examples, and try to solve other examples also, I mean other questions also, and be ready, be prepared. And if you have any doubt, you can contact me through my WhatsApp number. I think all of you have, I mean most of you have got my number. Otherwise, you can take it from your neighbors in this social platform. I can't reveal my phone number, sorry. So you can take it from your friends, and if you have any doubt, genuine doubt, you can contact me through WhatsApp, no problem. And if you can ask some questions and queries also, no problem, it is invited. And be prepared, and don't keep any doubts with you. Any doubts, you can consult with me, no problem. So be prepared, and do well, keep well, be safe at home, eat well, and be healthy. Okay, we will meet again. Bye.